Oh, okay. So I can start.
Yes, you can start your presentation, Doctor.
So, my report is devoted to the influence of the sun on self-organization of water molecules and to the ability of bulk water to copy and reproduce the size of its clusters and other molecules. This phenomenon sheds light on water memory phenomenon. The mass of the sun is 750 times larger than the mass of all planets rotating around it. And the Earth, compared to the sun, is just a fine grain of sand. The solar energy exerts a strong influence on the Earth. It is sufficient to say that even the earthquakes on the Earth are modulated by the sun. This slide displays the influence of the solar wind, which is a stream of particles, mainly electrons and protons. In contrast to electromagnetic oscillations, the solar wind is absorbed by the atmosphere and doesn't reach the surface of the Earth. Nevertheless, the solar wind exerts a very strong influence on the Earth. In the upper atmosphere, the solar wind generates secondary particles, muons. We have found that self-organization of water molecules and the stability of water clusters strongly depend on the intensity of muon flow, which constantly changes depending on the variations of solar activity and distribution of solar energy due to the rotation of the Earth around its axis and around the sun. We have devised a chemical method which allows measuring the influence of the sun very precisely. This method is shown here. On mixing water with acetonitrile, we do not receive a solution of single water molecules in acetonitrile. Instead of this, the formation of water clusters in acetonitrile takes place. We have found that muons generated by the solar wind destroy water clusters, and when the solar influence decreases, clusters reunite again. Small clusters are chemically much more reactive than large ones. That is why, under the constantly changing influence of muons, the same solution of water in acetonitrile can have different chemical reactivity, because it can consist of small number of large passive clusters or large number of small active clusters. To determine quantitatively the chemical reactivity of water clusters under the influence of muons proved possible by measuring the rate of hydrolysis of triethyl phosphite 1 into diethyl phosphonate 2. This conversion rate can be quickly and accurately measured by phosphorus NMR spectroscopy. We have found that this reaction depends on the rotation of the Earth around its axis and doesn't obey the law of chemical thermodynamics. At constant temperature and concentration, the rate of this reaction depends on the position of the sun in the sky, and this displays distinct diurnal variations. In the morning, the reaction rate is lower and rises by noon up to 2-4 times, and then it slows down again. We noticed that the range of diurnal changes is not constant and can vary on different days throughout the year. In summer, when the solar influence is higher, the diurnal variations are more pronounced than in winter. That is why we made a supposition that the rate of hydrolysis may depend also on the rotation of the Earth around the Sun. For this reason, in January 2015, we started regular measurements of the rate of hydrolysis of triethyl phosphite in acetonitrile. This year was in the middle of the 11-year solar cycle, and the solar activity was higher. It was found that this reaction, highly dynamic, and its rate displays very large annual variations. In January, the reaction was slow, as you can see on this picture, and started to grow gradually in March. At the end of June, a sharp rise occurred, and in early July, the reaction rate became very high. From September till the end of the year, the reaction rate slowed down again. The acceleration of the hydrolysis rate in summer and slowing down in winter means that influence of the sun on water molecules depends on geographic latitude and can be different in the northern and southern hemisphere. Further measurements showed that the annual variations in the rate of this reaction are different each year and correlate with the variations of solar activity during 11-year solar cycle. The rate of hydrolysis of triethyl phosphite in acetonitrile can change within a very wide range. The difference between single experiments between January and July can reach 200 times. In 2016, a very strong summer acceleration of this reaction took place again. In this year, the acceleration was very intensive already in April and May, and it lasted till the end of July. In September, one more acceleration of a shorter duration and smaller intensity took place. In 2017, the rate of this reaction remained very dynamic, but the annual difference between winter and summer rates became less pronounced. That year, another interesting phenomenon was observed. On August 21 in 2017, a solar eclipse took place, and immediately after this, the rate of hydrolysis decreased sharply for 5 days. This you can see here. In 2018, the slowing down of the reaction became very strong. Against the background of low rate 4 times in June, July, November, and December, the extremely sharp accelerations of short duration took place, which could be caused by the coronal mass ejections on the sun. In 2019, a further decrease of the rate of hydrolysis was observed. The summer acceleration took place again, however, it was much less pronounced. Thus, regular 5-year measurements showed that the annual rate variations are different every year, and from 2015 to 2019, a general deceleration of the reaction took place. This deceleration is in a good agreement with the decline in solar activity in the 24th 11-year solar cycle, which started in December 2008 and ended in December 2019. In January 2020, the new 25th cycle began, and the solar activity started to grow. In the first 5 months, the rate of this reaction remained low, and then it started to grow very intensively. These results convincingly confirm that the water activity is modulated by the 11-year solar cycles. Thus, the solar wind influence water clusters by means of muons. This is confirmed by the following. Muon flow displays the same diurnal and annual variations as hydrolysis rate. Underground, the hydrolysis slows down considerably. Muon flux is anisotropic, so the rate of hydrolysis depends on the position of the sun in the sky. These numerous, almost daily experiments yielded another very interesting and unusual result, caused by the anisotropy of the muon flux. We noticed that the same reaction solution has different reaction rate in 5 mm NMR tubes and in 20 milliliter jar, as you see on this slide. This difference is constantly changing and can reach 5 times. The difference between these vessels is their geometry. The jar has a much larger top surface than this vertical NMR tube. Since the muon flow is anisotropic and means that the vertical and horizontal muon flux should exert different influences on the jar and on the NMR tube. Analyzing these results, it was logical to assume that the influence of muons on water clusters should depend not only on the geometry of a solution, but also on its position in space. And the reaction should have different rates in 5 mm NMR tubes directed vertically and horizontally, since the upper surface in a horizontal tube is much larger than in the vertical one. And indeed, this assumption was easily confirmed experimentally. The rate of hydrolysis in multi-directional tubes are always different. This difference depends on the position of the sun in the sky and changes during the day. At noon, when the sun shines perpendicular to the horizontal tubes, the rate in them is the highest, while the vertical tube, in the vertical tube, it is the smallest, and this difference can reach 6 times. And at sunset, the sun shines along the east-west line, perpendicular to the vertical tube, and the rate ratio becomes opposite. The highest rate at the sunset in the vertical tube, and the smallest rate in the east-west tube. Thus, the solar wind destroys water clusters through muons. This explains the water memory mystery. Water memory is the ability of bulk water to copy and reproduce the size of its clusters and other molecules. However, this phenomenon is considered unproven because it is not always reproducible. No one could have imagined that the solar influence is the cause of this instability. Water memory can only sustainably manifest itself during periods of low solar influence when water clusters are stable. We have confirmed this experimentally. This slide shows how we performed the hydrolysis of triethyl phosphite experimentally. First, we added water to acetonitrile, which contained 0.02% of water, and then added triethyl phosphite. Under the direct strong influence, the solution of water in acetonitrile consists of a large number of destroyed small active clusters, and hydrolysis proceeds rapidly. And underground, the influence of muons is weak. Clusters are large, not destroyed, and with a small number of large passive clusters, the same reaction is slow. In these experiments, we used commercial acetonitrile, which contained 0.02% of water. After numerous experiments, we discovered an amazing phenomenon. The rate of hydrolysis depends on the place of location of acetonitrile before mixing it with water. For example, if acetonitrile was under the sun influence, then after adding water, solution contained a lot of small active clusters and the reaction was very high. And if the acetonitrile was underground or in the basement of for example, of a large building, then after adding water, very large clusters were obtained, and the reaction with acetonitrile was very low. The admixture of water in acetonitrile also self-organizes in different ways upon contact with different substances. For example, with metals. Upon contact with aluminium and molybdenum, the size of clusters in acetonitrile decreases, and upon contact with copper, silver, or iron, it greatly increases. For example, after contact of acetonitrile with aluminium or copper, the added water will hydrolyze triethyl phosphite with the rate of difference up to 500 times. After these results, we supposed that bulk water in acetonitrile could copy the size of organic molecules. And indeed, this is easily confirmed experimentally on the example of sugar. If 0.5% of sugar is added to acetonitrile, and then water and triethyl phosphate are added, then the hydrolysis rate will be 3-4 times less than in the same experiment without sugar. The copying is stably reproducible during periods of low solar influence. And when the muon flux increases and destroy water clusters, for example, in June, July, sugar coping is not always reproducible. The obtained results explain the mystery of water memory, which is also not always reproducible. Bulk water can copy and reproduce the size of its clusters and other molecules. And water memory phenomenon does exist, but it can only manifest itself under weak solar influence when water clusters are stable. Other conclusions are the ability of water molecules to self-organize strongly depends on the influence of the sun and on geographic latitude. Measurements of the chemical reactivity of water clusters in different places can provide important information about the impact of space weather on the Earth. Now, this is all what I wanted to tell you. Thank you very much for your attention, and I'm grateful to the Alexander von Humboldt Foundation for supporting this research. Thank you very much.